we know that voltage is IR. Okay. Well, voltage, okay, this is going to be the energy per charge. And so the question would be, therefore, what about the rate of change of energy? So let's VQ equals U. So I want to know power. Power is rate of change of energy. So I take a derivative of both sides here. And so the power is going to, if the voltage stays constant, that'll be dq dt. Well, dq dt is just current. So P equals IV. All right, so here we have a relationship for power. Power equals IV. That's true. Well, we know V equals IR, so we can also say P equals I squared R. Okay, so that's another way of saying the same thing. Or I equals V over R, so that means power is V squared over R. Okay, so these are three different ways of saying the same thing. Why would we care? Well, several things. First of all, assuming that you want to have a heating element. So you want to have an electric heater. So you want to have an electric heater here, and the voltage is constant. So in other words, you want to plug it into the wall, 120 volts. You want an electric heater. Do you want something with high resistance or low resistance? So you look over here. V is constant. So to get high power, you need low resistance. So that means an electric heater should be something with very low resistance. And that would give you the most electrical power dissipated over here. Okay. I times V, that's going to be a measure of the current being supplied. I squared R is going to be a measure of the current being dissipated. So if you know I, you know R, you know the power being dissipated. Okay, so example. In the early days of electricity, we had Thomas Edison, and Edison was insistent that we have direct current, so DC. So if you wanted to power something, you had to power it with a power supply. Now the problem is that you have some resistance right here, and then you have some resistance in the wires up here as well. Okay, so we'll call this R0, okay, if that's the resistance of your load, or I can call it RL, I suppose, for the load resistance, and then R is the resistance of the wires. So the total resistance, because the current has to go through both of those, so the total resistance is going to be equal to R plus RL. We'll talk about this later, how series circuits work. But that's the total resistance right here. So that's the total resistance. And so that means that the power, if we have electrical current going through here, the power I squared R, that's the power being dissipated here, RL, but I squared R is also being dissipated in the wires. So if the wires have about the same resistance as the load, that means that you're wasting half of your power in the wires instead of in the load, which means you have to have twice as much power being supplied up here. Well, resistance is rho L over A. So the longer the wire, the bigger the resistance. And so that means for DC, which Edison liked, you have to have fairly short wires. That means you have to have a power plant for every neighborhood. Now, Nikola Tesla had a different idea. He wanted to use AC, so this is changing voltage. Now, the advantage of AC is it allows you to use something called a transformer. And the way a transformer works is it transforms the power to a different voltage. Okay. and then we can have a transformer here, okay, and then we have our load resistor. Okay, now why of this of any interest? Okay, with DC you cannot have a transformer, so that means if you've got a load resistor here and wires, and the wires, if the wires have a resistance that's 10 times the load resistance, okay, then that means that I squared R, okay, you have 10 times the power dissipated in the wires as in your load. Okay, but power equals IV. So that means if you increase the voltage, you decrease the current for the same power. So in other words, you might have 100 watts here. Okay, if you have 100 watts at 100 volts, that's going to be 1 amp. And so the 1 amp is both in the wires and in the load. But if you have 100 watts at 100 volts, that's 1 amp right here. But if we instead go to 100 kilowatts, or let's make it 10 kilowatts. If we go to 10 kilowatts, then 10 kilowatts is going to be 100 times more. So that means that the current is going to be 100 times less. So that means 0.01 amps. So 0.01 amps is going to have times 10 kilowatts is going to be the same as 100 volts times 1 amp. Okay. Well, I squared R means if you decrease by 100 the current, you decrease by 10,000 the amount of power dissipated in those wires. And then you have a step-down transformer that goes from 10 kilowatts down to 100 volts, so that's back to 1 amp. Okay, so now we get 1 amp over here, gives us the current and power we expect on the load. So that only worked with AC. Okay, and so this was a huge argument in the early days of electricity between DC, which was Thomas Edison, or AC, which was Nikola Tesla. And turns out that a single power plant through economy of scale is easier and cheaper to operate than a whole bunch of power plants. And so AC power won, even though it was generally regarded as being less safe than DC power. But this is where these different ideas of power and those three equations come in. Okay, so with that, I've covered most of the theory behind chapter 26. And so now it is primarily just a matter of applying this. So then I'm going to start doing a whole bunch of example problems.